All right, everybody. So, welcome back. It's been a while since I've seen you all. As far as the class moving forward goes, we're going to switch back to the sort of traditional lecture and then homework format. You're going to get your final homework assignments posted later today, and it'll be due on December 8th, the last day of class. I want to quickly sort of map out what the rest of the semester is going to look like. Today we are going to be covering, or starting to cover, fluid dynamics. Fluid dynamics is the study of fluid flow. So in the past couple of classes, you've been looking at fluid statics, where our fluids are stationary. We look at things like pressure, our Archimedes principle. We look at buoyancy. That's all statics. Our fluids are not moving. In this lecture and the next one, we'll be talking about what happens when fluids start to flow. You get very interesting behavior. After fluid dynamics, we're going to cover our last topic of the semester, oscillations. We're going to look at something called a simple harmonic oscillator. That's a special type of device that gives us very predictable behavior. Why do we study simple harmonic oscillators? Well, it turns out simple harmonic oscillators exist all over the place. Everywhere from what makes cells work, how we transport things through cells, to how galaxies move. They all deal with simple harmonic oscillations. So a very powerful mathematical tool to cover. And we'll look at oscillations. Time permitted, we'll probably have a lecture on waves, but there will not be a question on the final on waves. It's more of just for your information, how waves work, and it's useful to know going into next semester, where we'll talk a little bit about something called electromagnetic waves. So having some familiarity with waves will be useful, but again, not going to test you. And that leads us into the final exam. The final exam, which will take place on December 8th. Our final exam will take place on December 8th, and it will cover collisions. So there'll be a problem with collisions. Thanks to the lab that we are doing today. There will be a problem involving fluid statics and fluid dynamics. So I'm going to build those into the same problem. And then there will be a problem on oscillations. So an object that undergoes some oscillatory motion. That will be the three problems on the final exam. Next week I will do a review session sort of thing on the Wednesday. What would that be? December 3rd? Something like that, yeah. So on December 3rd, we'll go ahead and do a review session similar to what we've done in previous exams. And that should take us all the way to the winter break. Are there any questions, thoughts, comments? Feel okay about this? Yes? What's up?
What time is the final exam?
I think it's scheduled for, I need to get back to you on that, because I think it is scheduled for this same time period. But let me get back to you on that. I need to double check. Any other questions? Oh, wonderful. So, that brings us to the question of fluid dynamics. When we look at fluid dynamics, we're looking at fluid flow, and the easiest place to start is by looking at a pipe that will carry some water. Now, under the context of fluid dynamics that we are studying, we are going to consider our fluids to be incompressible. When fluids are incompressible, that means that their density must maintain some constant value. So fluids, which includes any material that flows, typically are considered liquids and gases. While fluids are liquids and gases, and plasmas as well, we are going to constrain ourselves to looking at specifically incompressible fluids. The density is a constant, and these are traditionally going to be considered liquids. Gases are compressible. I mean, if you've ever been in a chemistry lab, you've seen those containers of compressed gases. That is because we can change their density. We can compress them to have a higher density. That is not what we're looking at today. And when we look at these fluids, well, we can sort of zoom in on the microscopic scale. On the microscopic scale, what we can do is apply pressure such as that the individual molecules will move throughout the container from left to right. But the problem with thinking about molecules is that there are Avogadro's number of these molecules. So instead what we're going to be doing is not looking at the individual molecules moving, but we're going to zoom out, we're going to look more macroscopic, and I'm going to say there's some section of fluid that we can map out, and this section of fluid will flow down the pipe over time with some velocity. And that velocity is going to be essentially the average velocity of all of the molecules that exist in this section of fluid, in this section of liquid. So we consider this section of liquid, and we're going to look at how that liquid moves throughout the pipe. That sound okay? All right. Now, we can talk about the speed of fluid meters per second, but oftentimes we talk about speed of fluid in a different way. In our day-to-day interactions with fluid, we might be concerned with not meters per second, but how much volume of liquid passes through the pipe over a given time. If you take a look at your shower head as if you replace a shower head and you look at your shower head and you want to know how quickly does water come out, well, you're not looking at meters per second, you're looking at liters per second, or gallons per second, right? Gallons per minute, more likely. And that idea of gallons per minute is what we define to be the rate of flow for a fluid. So when we talk about fluid motion, most of the time in our day-to-day life, we talk about it in terms of this fluid flow. This fluid flow, which tells us the volume of fluid moving through a pipe, in this case, moving through a pipe in some given amount of time. How quickly does a volume of water flow through? Gallons is a volume of water. How many gallons of fluid flow through a pipe in a minute? Gallons per minute. Or liters per second, if we want it to be SI units. Does this sound okay? All right, well, how do we figure this out? How do we figure this out? Well, we take a look at this volume of water. We say that this pipe has some area, A, and that volume of, I'm going to use the word water here, but it does apply to any liquid, it's just my brain thinks automatically with water. The area of this pipe is the same as the area of this section of fluid that we're looking at, right? So we have some area. Well, this pipe is cylindrical, meaning I can find the volume by looking at that area and multiplying it by the distance inside we're looking at, some delta x. Sound good? At which point, we can rewrite this volume as being area times delta x. This is just the volume of the cylinder. Not so bad, yeah? We continue to take a look at this and we say, okay, well, we divide that by time. What is this time, though? This time that we are looking at is the amount of time it takes for this volume of water to move past this end line to get this total volume of water to flow forward. So we start off in this initial red region. I'll say that's initial. Sometime later, all of that volume of fluid will move forward to cover a new area of the pipe. So it goes from this red region, that water flows forward and will eventually make it to this blue area. Can we visualize that? Yeah? And this is our final position. And T is the amount of time to make that flow occur. T is the amount of time to have that flow move from that red region to the blue region. That is the time, that is our delta T that we look for. So we have our defined flow rate, volume over time. Defined flow rate, the definition of flow rate is volume over time, and we become more specific with our scenario by saying our volume is that of a cylinder, and the time is the amount of time to get that fluid to move completely from one segment to the next. So that gives us our delta T. Now this is interesting because we're seeing something that might be familiar. Delta X over delta T. Delta X over delta T, we've seen that before. Where have we seen that before? What is that?
Velocity.
Velocity. Velocity, what is it? It's velocity, the velocity of our fluid. The actual velocity of our fluid, meaning essentially the average of all of the molecules' velocities. This is the average velocity of our fluid. So we could do A times V. Now we need to be careful here, because we're running into a region where we have V representing two different values. We have V representing volume in certain situations and V representing velocity. To denote volume, I will typically use V with a serifs on it, so that's a capital V. And for velocity, I will use V sans serif to indicate our smaller velocity. Sound good? So you want to know what the flow rate of your fluid is? How quickly does it move through the pipe? You can calculate it two ways. You can look at some volume of it and divide that by delta T. But this introduces two things. It introduces the idea, well, how big is the volume you look at? And that changes with T. So maybe that's not the best way to go about it. Or you can look at it as a cross-sectional area of the pipe, something that is unchanging. And the velocity, something that doesn't depend on how much fluid you look at, because it is just the speed that the fluid is going at. But these are both ways to calculate your flow rates. All right, any questions? Any thoughts and comments? So we're just starting to dive into this idea of fluid dynamics, where we define a way to quantify our fluid flow. Our fluid flows with this rate Q, which is volume of fluid divided by some delta T, how long it takes for that fluid to flow entirely to the next segment of the pipe, or we can define it as the area of the pipe multiplied by the speed of that fluid. Okay, I'm just going to start from scratch. Because now we're going to look at what happens when there are changes to the system that constrains our fluid. When we put constraints on our fluid, we can change those constraints, and the constraint here was a pipe, but what we can do is we can take a pipe and we can feed a large pipe into a smaller region. So we start with a large pipe and we feed it into a smaller region. Essentially, we funnel all of this fluid into a smaller region. Now, when we talk about the flow rates of our fluid, we need to remember something important about our fluid. It's that it's incompressible, that our fluid cannot be compressed to a smaller volume. So when we look over here and we define some fluid, some region of fluid, perhaps in this red area, we say here is some volume of fluid filled in with this red. This volume of fluid has some distance delta x and some area A for our cross-sectional area. And we take a look at this and we say, well, this will cover some distance in some time, delta t, and we can define Q as being area times delta x divided by delta t. No problem. But when we take a look at this fluid as it flows down the pipe, it's going to start to become constrained more and more. And for it to have the same volume in this thinner area, it's going to need a much larger delta x. So our fluid, which took up a small width because of the large area, as it constrains to a smaller area, it has to have a larger width. Again, it cannot be compressed to a smaller volume. The volume must be the same in each case. The volume must be the same in each case. Does this sound reasonable? Yes? All right, we take a look at this. We take a look at the individual molecules of fluid. We zoom in. We zoom in, and we look at the molecule that is going to be just on that trailing edge of the red line. If our molecule is on just the very trailing edge of this red line, and we want all of the molecules to move forward to the next segment, that means this molecule will travel a distance, delta x, in an amount of time, delta t. So we can say that the velocity here for this trailing molecule is going to be delta x over delta t. Nothing too crazy. Sound good? But we look at this next stage. And we say here is a molecule on the trailing edge of this blue region. And it's going to need to move forward to that new distance, delta x. It's going to travel a lot further to get to the next segment of type, right? This molecule has to travel much further horizontally to get to the next segment than the molecule in the red region. But we go back to the idea that this fluid must be incompressible. What does that mean? That means as this fluid moves forward, it pushes this fluid forward as well. We can't have any fluid bunching up. So that means that it must take the same amount of time for the fluid to flow through each section. If it didn't, if it took longer for the molecule in the blue region to transfer from left to right than it did for the red region, then you'll get molecules bunching up in this smaller region, and that would cause it to compress, but we say we don't allow that. Since we don't allow that, that means it must take the same amount of time for a molecule in this trailing part of the red region to make it all the way through the red region, as it would for the molecule in the blue region to make it all the way through the blue region. It must take the same amount of time. Well, if both of our molecules travels with the same delta t, but the blue region has a larger delta x, what can we say about the individual velocities? Is the velocity in the blue region larger or smaller than the velocity in the red region? Must be greater. The fluid must travel more quickly in the region that has a smaller area. So that tells us that we have a large velocity and a small velocity for the blue and red regions, respectively. And this is something that I think, are probably pretty familiar with, because if you've ever played with a garden hose and you've left the garden hose wide open, the water comes out pretty slowly. But if you put your thumb over and cover up a large portion of the area, if you constrain the water, it starts to come out more quickly. Yes? That is because of this effect that says that the fluid must move through the regions at the same rate, the same amount of time, despite the fact that the area in the more constrained region is going to be smaller. Does that sound okay? All right, well, can we quantify this? Can we put numbers to this? Can we start to do mathematics with this? And the answer is absolutely, of course we can. We wouldn't be doing this exercise if we couldn't. So I'm going to draw a new diagram here. Same system, same pipe going into a thinner pipe. And I'm going to draw what is commonly considered a flow diagram. A flow diagram will take arrows and run arrows all the way through our system to represent our fluid flow. And why do we do this? We do this because our fluid must flow entirely throughout this pipe. And in the region, if we have 3 arrows in our larger region, we must have the same 3 arrows in the smaller region. Now when we do this, we can start to identify some behaviors that will become more useful to us a little bit later in the lecture. But we see that as we get in the more constrained region, our arrows are closer together. And this is common for what we would call a vector field. That's just a fancy way of saying representations of vector quantities with arrows. We'll see a lot of that next semester. But the closer they are together, the larger some physical quantity is. In this case, physical quantity is velocity. So how close the arrows are tell us about the speed that the fluids are moving at. So we have our velocity being larger where the arrows are more closely tied together. But what this also allows us to do is it allows us to see every single molecule that passes through. These lines are like representations of the motion of molecules. Every single molecule that passes through this larger region must pass through the smaller region. And what does that mean? That means we calculate some quantity for the flow rate in the larger region. Well, that flow rate tells us about how much volume, how much matter or fluid moves through this large region. It must be the same exact flow rate in the smaller region. Because the water is not disappearing, the fluid inside of the system is not disappearing, it's not magically being created. So any fluid that flows through the larger region must also be flowing through the smaller region. So what that tells us is that this flow rate, which we can calculate by taking area times dx over delta t, or area times velocity, this flow rate which we can calculate must be constant throughout this system, so long as we're not putting new fluid in and taking fluid out. So we label the larger area, area 1. We label the smaller area, area 2. And what we could say is that in the first region, in region 1, we calculate a flow rate Q1, which is equal to area 1 times the speed of the fluid in that region. We look at area 2, and in the second area, we calculate a flow rate Q2, which is area 2 times speed in that second area. And for the cases of fluids, we can not worry too much about the fact that velocity is a vector. We can consider really speed because our fluid, it's always going to flow in the direction of the pipe. So direction kind of doesn't matter a whole lot here. But knowing that all the fluid must flow through each region tells us that the flow rates must be the same, meaning Q1 must equal Q2. The flow rate in area 1 is equal to the flow rate in area 2. This is what we call continuity. In physics, we have a bunch of continuity equations. This is just one of them. And it tells us that the fluid must continuously flow through our system. And we take a look at this and we say, well, area 1, V1, must equal area 2, velocity 2, or speed 2. And that's the equation for continuity of our fluid flow. Are there any questions about that? Any thoughts? So you say, okay, what kind of problems can we come up with? What kind of problems we can come up with? Well, let's imagine a situation where we have a hose, and our hose has a 5-centimeter diameter. Our hose has a 5-centimeter diameter, and we have water coming out of the hose at a speed of you know, it'll give us 2 sig figs, 5.0, 3.0. And we have water coming out of the hose at 3 meters per second. So here is our hose, water exiting, and some diameter. With this, we can calculate some flow rates. Q1, we'll do that shortly, equals some value. Now again, I said that if you've ever played with a garden hose and you've ever covered the end, you'll see that it speeds up. It speeds up the fluid. So let's say we cover up part of the end of our garden hose. What does that do? It effectively reduces the area the fluid can flow through. Reducing the area, if we decrease the area, in response to that, the speed must increase, exactly what we were saying earlier. And I'm going to say we decrease it by area 2 is equal to 0.3 times area 1. We decrease it by 70%. The question is, how much faster is the water moving through this? Now, there's a quick way to get here. I'll show you the quick way. But we'll do it step by step just for the practice of it. And so if we have a hose of 5 centimeter diameter that has water normally flowing out at 3 meters per second, the question is, how quickly does water leave the hose if we cover 70% of the end of the hose? Going step by step, again, just for the practice of it, we could first calculate out the flow rates in the hose when it is not covered. When it is not covered, how do we calculate flow rate? Area times speed. Well, the area of a hose is generally a circle. So the area of a circle, what is it? Pi r squared. We don't have the radius though. We have the diameter, so pi times diameter squared over 4. Or you can use radius 2.5, doesn't really matter. But we have our area, pi diameter squared over 4. We multiply this by the velocity. That gives us our flow rate. It gives us our flow rate. We calculate it out, right? But the problem here, our diameter is in centimeters, our velocity is in meters per second. Most likely, we want to do some unit conversions. So let's go ahead and do our unit conversions. We'll have pi times our diameter, 5 times 10 to the minus 2 meters squared over 4. Multiply that by 3 meters per second. I'm neglecting the point zeros there. They do exist. They do tell us something about significant figures, but we'll leave it at that for the calculation portion. So what is our flow rate in region 1? What is the flow rate in the hose that is the part of the hose that is unobstructed? Calculate it out.
Is it a small number?
Missing something here?
It's 5.9.
Okay, 5.9. Missing something though, what are we missing? Units, what are the units? Meters cubed per second. So should this be a small number? Should we expect a small number? And when we are in this unit of meters cubed per second, let's imagine what a meter cubed of water is. Take a meter stick, take a meter stick and we imagine the volume of a meter stick by a meter stick by a meter stick, a huge cube of water. A meter cubed is a large volume. And we imagine, can we fill up a meter cubed container of water in a second with a garden hose? Probably not. So the answer is, yeah, we should expect this to be a small number because meter cubed is a large value for volume, and seconds is a relatively small amount of time. So we should expect a small number if we are in units of meters cubed per second, absolutely. But this gives us our flow rate of our hose. This tells us the flow rate of our hose. Continuity. Continuity tells us that the flow rate in the unobstructed region is equal to the flow rate in the obstructed region. When we thin out our area, the flow rates must be the same. So what does that tell us? It tells us the flow rate in area 2 is the same, 0.0059 meters cubed per second. Doesn't matter that we've decreased the area, the flow rate must be the same. But we also know that the flow rate is defined to be area times speed. So if we want to know how fast the fluid leaves the hose width, well, we can take this and we can solve it for V2. So velocity 2 is equal to flow rate in the obstructed region where we cover the tip of the hose, and we divide it by area 2. 0.0059 meters cubed per second divided by the area 2, pi times diameter squared over 4, we don't have a circle, right? So it's not pi times diameter squared over 4. Instead, what we know it to be is 0.3 times area 1. Area 2 is 30% of area 1. We decreased it by 70%. Area 1, of course, pi times diameter, 10 to the minus 2 squared over 4. Fractions and fractions, math teacher would have a heart attack. But this should give you the speed of our fluid moving through the obstructed region. Calculate that out. All right, do we have an answer for what the speed is moving through the obstructed region? .5 meters per second? Doesn't sound right to me. You got 10? Ten meters per second. 10 meters per second. So we have an increased velocity, or increased velocity sounds good to me. Now we went through this process of calculating flow rate, and from finding our flow rate, figuring out what the velocity in 2 is, there was a quicker way. There was a quicker way if we start off with the equation of continuity. Our equation of continuity says area 1, velocity 1 is equal to area 2, velocity 2. We want to know what velocity 2 is. We say velocity 2 is area 1 over area 2 times velocity 1. Area 2 is 0.3 times area 1. Area 1 cancels out, so you get velocity 1 divided by 0.3. And when you take 3 and you divide by 0.3, what do you get? You get 10. So there was a quicker way to do it, but I went through this process of finding our flow rates. I went through this process of finding our flow rates so that we can determine other physics problems that might be of interest if we just consider flow rates. So we're going to look at a new problem. We're going to take our garden hose, but I'm going to change our garden hose. We're not going to obstruct it. I'm going to change our garden hose to have a little bit faster of a fluid speed. I'm going to say that it has a fluid speed of 5.5 meters per second. Why did I do that? Because I'm going to have you calculate a flow rate again for this next problem. So what I want us to do is calculate how long to fill an Olympic swimming pool with this hose. How long does it take to fill an Olympic swimming pool with this hose? Now, Olympic swimming pools have a length of 50 meters. A width of 25 meters, and a depth of, at minimum, 2 meters. We'll take the minimum of 2 meters. So we start to make predictions. We start to make predictions about physical reality. How long does it take to make something happen? How long does it take to fill a pool, given the constraints of our system, given the constraints of a hose that allows fluid to flow out at some rates? So how do we figure this out? Well, our fluid rate was defined to be written in two ways. We can write it as area times velocity, but there was another way to write our fluid rate, which is volume over time. When we take a look at this, we can calculate our flow rate of our hose, area times velocity. We just did that with a different speed. Our flow rate should be a little bit higher now than it was before. The volume we are looking at, well, the volume I want to know about is the volume of water that fills an Olympic swimming pool, length times width times height. I want to know how long does it take? How long does it take? Do we feel like we can solve this problem? Is there any questions? All right. I want you to find the answer, and I want you to specifically find the answer in reasonable units. What does that mean? That means I want the time to be in a reasonable unit. I don't want 5 billion seconds or whatever it is. I want a reasonable unit, minutes, hours, days, whatever the answer might be. I'm going to give you guys a few minutes to try that on your own, and then we'll come together as a class. Remember, I changed the speed to 5.5 meters per second, so your flow rate is now different than it was in the earlier problem. I did this to make you recalculate flow rates. Let's do some unit conversion practice. Raise your hand if you want some more time. All right, give you a little bit longer. All right, so let's go ahead and talk through this problem. So we know our flow rates can be calculated two ways. Area of our pipe or our hose times the speed that fluid moves through our hose. Or we can calculate it as volume over time, V over delta T. Now again, here I use V with the serif to represent volume, sans serif means velocity. And here what I want is delta T, so we solve this for delta T is equal to volume divided by area times velocity. Volume, well, it's the volume of water which we care about, is the volume of water in our Olympic swimming pool, length times width times height. And we divide that by the area of our hose, which is going to be pi times diameter squared over 4. We multiply that by the velocity, 5.5 meters per second. Now you can calculate out the flow rate first and plug the flow rate into the bottom of the fraction here. I'm just doing this all in one step. Calculate this out. You'll find it's a lot of seconds, big number of hours, or about 2.6, 2.7 days. 2.6? 2.7, somewhere in that. I think it's actually 2 2/3 days. So it's about 2 days, 16 hours to fill up the swimming pool with a garden hose. Pretty unreasonable. Pretty unreasonable. That's why you don't actually fill up Olympic swimming pools with a garden hose. But this gives you an accurate idea of how long it would take to fill up a pool with water. Are there any questions on this? All right. Now, when we talk about fluid flow rates, this is inherently a kinematic property, meaning it's a property that details for us how to discuss the motion of fluid, how to discuss how quickly fluid moves throughout a container, but it neglects the question of what causes fluid to move through the container. If we want a discussion on what causes fluid to move through the containers, we are now looking at dynamics. And this is the dynamics part of when we talk about fluid dynamics, what causes fluid to flow. So let's imagine a pipe. And let's say this pipe is filled with fluid. Now, if we were to just let go of the pipe, the fluid wouldn't flow in either direction. If we just say, here's a pipe filled with fluids, if both of the ends are open, what's going to happen? The fluid is going to flow out of both sides of the pipe. We're not going to really get flow in any specific direction. If we want to introduce flow in a specific direction, what we have to do is apply pressure to one side of the pipe. If you apply pressure, that starts to force the fluid through the pipe, yes? But important note here, important caveat, is that pressure does exert on both sides. You always have pressure on either side, unless you have an absolute vacuum, which doesn't really exist. You will always have pressure on either side. So really what you're looking for here is some sort of a change in pressure gradient. Get some sort of a change in pressure where the pressure on one side is larger than the other. When you start to have a difference in pressure on either side of the tube, that's when you start to get fluid to flow. If you think of a straw achieves the pressure difference by creating a vacuum when you suck through your mouth on the straw. It creates a vacuum getting the fluid to move to the lower pressure. When you think of a garden hose will have a higher pressure caused by the whatever reservoir is feeding your house, which is feeding the garden hose. So, in all cases, pressure differences will cause a flow of fluid. Now we think about how we can deal with this pressure. Okay, well I know pressure is defined as force divided by area. That's the definition of pressure. So this is how much force are we applying over some region. We say, okay, well I know force has to do with acceleration, so maybe I say F equals ma over area, but this starts to become more and more complicated. So we can't really apply Newton's laws to this case. Well, you can in theory, but it becomes much too difficult. So we're going to take a step back and say, okay, Newton's laws doesn't work super well. So what other methods do we have to perhaps determine our fluid flow behavior? Well, we've studied another way to look at dynamics. What was the other way? The Newton's laws failed us with like springs and stuff like that. Energy. Kinetic energy, potential energy, and work. Right? These are all ways we describe dynamics in other systems. So we'll do the same thing here. We'll start off with work. Why do we start off with work? Well, work tells us about a change in kinetic energy, provided there are no potential energies in the system, and for right now we will assume no potential energies in the system. So if we can figure out the work, we can say something about the speed, and if we could say something about the speed, we can say something about the flow rate. So it seems like a good first step. Look at this and we say, okay, well how do I describe the work? Work is equal to force times distance, F delta x. Reasonable enough. I know that force is pressure times area, we do want to get it into this pressure notation, because when we talk about fluids, ultimately what we're talking about is not forces, but pressures. So you say pressure times area, where area is the cross-sectional area of our pipe, multiply that by delta x being how far have we moved the fluid with our pressure. That sound okay? All right. Now, taking a look at this area times delta x. Taking a look at this area times delta x. If we are looking at taking this volume of fluid and moving it from one end of the container to the other, the delta x we are moving it is the length of our container. Yes? The area, cross-sectional area of our pipe, meaning when we take that area and multiply it by delta x, what does that tell us? Volume. It tells you the volume. So instead what we can actually write this as is pressure times volume. Yes? All right. Now, we're going to get a little more specific. Work done from the left pressure. Work done from the left pressure. On the left-hand side, we have some pressure pushing to the right. So we could write this as positive pressure times volume. Because it's moving the fluid rightward, so it makes sense. So let's use positive in that case. Then we look at the pressure on the right-hand side, because we do have pressure on the right-hand side. We always have pressure on either side of our container. So pressure on the right-hand side would give us some other amount of work. And I will say this is pressure on the left times volume. And that pressure is trying to counteract the pressure on the left. Since it's trying to counteract it, I'll put a negative there. So you have pressure on the left giving us an amount of work equal to positive PV, and then negative PV on the right. And there are going to be different pressures. Again, you need some pressure difference between the two to get fluid to flow. So P left and P right are going to be different values. And we combine these two, like we did when we were looking at multiple forces acting on an object. We combine these to give us the total amount of work. The total amount of work being the combination P left times volume minus P right times volume. Or, let's go ahead and rewrite that. Let's go ahead and rewrite that as the change in pressure delta P times volume. And again, this tells us that some amount of work is done when we have a change in pressure. Some amount of work is done when we have a change in pressure. And if work is done, then our fluid starts to move. If our fluid starts to move, we start to have kinetic energy, energy of motion, that is equal to that work done. So we say work is equal to your change in kinetic energy. Now here our change isn't initial and final, our change is going to be left and right. But our work gives us our kinetic energy. Our work is going to be change in pressure times volume. Kinetic energy is going to be half mv squared, bless you. Half mv, we'll assume initial 0 just for simplicity right now. For simplicity, we'll say it's equal to 0. Feel okay? Any thoughts, any comments? We take this, and I'm going to say change in pressure is 1/2 mass over volume times speed squared. Where V is how quickly it's moving at the end of the pipe. Mass is the mass of fluid inside of our system that is moving. V is the volume of fluid inside the system that's moving. Mass divided by volume. Mass divided by volume is a physical quantity. We should know what is mass divided by volume? Density. Density. So the change in pressure gives us 1/2 the density times V squared. And that tells us something. What does that tell us? It tells us that the actual volume of fluid that we're looking at doesn't matter. The only thing that matters here is what is the density of our fluid. And that tells us pressure, our change in pressure, is directly proportional to how quickly the fluid will be moving through our pipe. So our change in pressure is directly related to the speed our fluid flows through the pipe. This is the work kinetic energy theorem applied to fluids, where now we say the work is basically our change in pressure, the difference between pressure of the inlet and outlet of our pipe, and our kinetic energy is 1/2 the density times the volume squared. Or times the velocity squared, sorry. Okay, any questions, any thoughts? We're going to take this a step further. Because now what we are going to do is take our pipe and we are going to have it raise in height. Our pipe is going to raise in height. It's going to go from some lower level to some higher level. It's going to undergo some change in height. We'll call that height H. Raises some height H. Now when it does that, we start to have a change in potential energy, and specifically gravitational potential energy. We don't worry about springs when it comes to water, because if you ever put a spring in water, you know that they don't really interact too much. So really here we only have to worry about gravitational potential energy. So going back to work kinetic energy theorem, our work kinetic energy theorem says our change in pressure times volume is equal to 1/2 mass times velocity squared. But it's 1/2 velocity squared, our change in velocity, right? Because it is technically change in kinetic energy. So I'm going to define two things. I'm going to define this area, the lower area, to be region 1, the higher area to be region 2. So we have 1/2 mv2 squared minus 1/2 mv1 squared. So just being a little bit more complete now. I'm going to now break up this change in pressure to be the pressure in region 1 minus the pressure, I'm doing 2 minus 1. Final minus initial. Pressure 2 minus pressure 1 times volume is equal to 1/2 mv2 squared minus 1/2 mv1 squared. And I'm going somewhere, I promise. I'm going to take this, I'm going to rearrange it to find like terms, and when I do that, wait, did I do something wrong here? Yeah. Okay, so now what I'm going to do is I'm going to put like terms on either side, so we'll have 1/2 mv2 squared minus p2 times volume is equal to 1/2 mv1 squared minus p1 times volume, something like that. think it makes sense to do that. Should I split up the pressures? I don't know, probably. We'll find out. So what we have here, what we're starting to have is an equation that looks suspiciously like conservation of energy. And kind of doing a hand-wavy derivation here, I'm going to shoehorn in potential energy. I'm going to shoehorn potential energy into this and just go ahead and add an mgh on either side. So mgh1 plus 1/2 mass times velocity 2 squared, or sorry, h2, minus p2v is equal to same thing but with ones in the subscript. Now the next step we can do, both sides has this volume term. I'm going to divide volume from both sides. And again, on the right hand side we have all of the same pieces, just with ones in the subscript. Divide both sides by volume. And what that's going to give us is mass over volume. Mass over volume is density. Density times acceleration due to gravity times height 2 plus 1/2 density velocity 2 squared minus p2, no volume. And then on the right hand side you would have the same thing, just with ones in the subscript. You know what, I'll write it out. Yeah, we have some. Now, what does this tell us? This tells us, first, that all of the pieces in the initial case are equal to all of the pieces in the final case. Or when we say initial and final, we mean region 1 and region 2. Meaning the total sum of these values ends up being a conserved quantity. This is a restatement of conservation of energy. This is a restatement of conservation of energy, and our restatement of conservation of energy tells us that changes in heights and changes in pressure give us changes in velocity. This is what is known as oh my god, I'm going to spell this wrong. Hold on. Make sure I get this right. Sorry, not great at spelling French names. This is what is known as Bernoulli's equation. Bernoulli's equation is a restatement of conservation of energy as it applies to fluids. Now, again, this is where the hand-wavy part comes in. By convention, we do take the pressures to be positive. It has to do with directionality of forces. Not hugely important, but we do take pressures to be positive by convention. It ends up not making a huge difference mathematically, but it saves us a little bit of ease by taking the positive pressure. Now, Bernoulli's equation is a powerful, powerful tool. It tells us things like why does an aircraft fly? Why does a wing cause lift? It tells us things about how fluids flow in our bodies, the blood that flows through our veins. It tells us important information about things in our everyday life. If you have a curtain in your shower, you'll notice that your shower curtain tends to flex inwards into the bathtub as you take a shower. Why does it do that? Bernoulli's equations actually explain why. Bernoulli's equations explain why roofs get ripped off of houses in hurricanes. Very powerful tool. We will be working with this in the next section, doing some problem solving involving it. But these two pieces, continuity and Bernoulli's equations, tell us everything we really need to know about fluid dynamics as far as this class is concerned. Now, we have made a couple of very important distinctions. The first distinction, we are only considering incompressible fluids. It becomes a little bit more fuzzy when we start dealing with gases, because with gases our densities can't change. So really we're only looking at liquids, and more to the point, we're only looking at liquids that are relatively low in viscosity. When viscosity gets larger, things become a little bit more messy. But for viscosity, these are the two equations that dictate fluid dynamics. All right, are there any questions, thoughts, comments? Okay. Before you leave today, a couple of notes. I'm going to stay behind until about 1 o'clock, so we'll be in this room. If you have any questions, it's a good time to get your questions answered. If you have anything to turn in to me that you didn't turn in the last couple of weeks, do so before you leave. Up here, I have a sheet for your test reflections, should you choose to do them. And then I have your exam 3s to hand back. Listen up for your name as I call, so you can come and collect your exam. Be sure to collect a reflection, turn in any homework you have before you leave, and stick around for any questions, comments, or concerns that you may have.